Right, guys, this is kind of a whole new concept for us. Polar graphing is on this kind of crazy graph paper. Have you seen this somewhere?
No.
Never ever? Some of you have? It does kind of look like the unit circle, okay? All right, and it is actually, Tyler said it looks like the view from above Earth. They do use this for things like tracking planes, okay? It says here that air traffic controllers record the location of airplanes using distances and angles, okay? When we do rectangular coordinate system, we have a directed horizontal x value and a directed vertical distance that we called x and y. When we use this system, we've got some new vocabulary here today, okay? The origin is a fixed point called the pole. So this point is now called a pole. The polar axis is an initial ray from the pole, usually horizontal and usually directed towards the right, in which case it's basically the positive x-axis. Okay? The polar axis can be moved, but we're not going to move it. So the polar axis is going to be the positive x-axis here. And it says the polar coordinates are going to be in this form, r, comma, theta. All right? R is the directed distance from the pole, and theta is the directed angle from the axis. In other words, if we said 60 degrees was our theta value and an R value of 5 units, it would mean you went 60 degrees of rotation in the positive direction and out 5 units and stopped, okay? There isn't an arrow, that's just the direction that you've measured out. To graph, yeah, I kind of talked about that, I think. Well, let me go over this. It says, when a negative value indicates clockwise, so if we go this way, it's negative, nothing new there, right? If you rotate that way, it's negative. If R is positive, P lies on the terminal side of the angle. If R is negative, this is a new concept for us, okay? P lies on the ray opposite the terminal side. All right, I'm just going to do a couple quick examples to kind of familiarize you with this. So if you just pay attention, you don't have this. I'm just going to do a few examples. If I did 5 comma pi over 2, what this means, I always wish this went theta r, okay, because you have to do the rotation before you can go out the r value. So this means if I start here on my polar axis and I measure pi over 2 positive around this way, I'm now on this line. Everybody okay? This tells me how far out in distance I go from the origin or from the pole. 1, 2, 3, 4, 5. Basically, this is a radius of 5. I go out a radius of 5, and these are each a radius of 1, 2, 3, 4, 5. Does that make sense? Okay, so let's try some crazy business like 3 comma negative 3 pi over 4. All that does is change what? The direction, okay? Now, those of us who hate radians and have a hard time with this, you could change it to degrees, okay? Or if this is 3 pi over 4, we went past 90 and 1, 2, 3 more marks, right? So if we're going negative 3 pi over 4, it's going to go past 90 and then 3 more. Does that make sense? Or you could add 2 pi to it, and you'd get 5 pi over 4. But we're on this axis now, and a distance of 3 out would be 1, 2, 3 would be here. Does that seem all right? All right. Now here's the crazy one. All right. Negative, negative. Actually, let's do negative, positive first. I haven't done a negative at all. Let's do negative, positive. So this means go around to 7 pi over 6. So I'm going here. Everybody okay?
Yeah.
This negative r means that instead of, I'm now facing that 7 pi over 6, okay? Instead of moving out this way, the negative means I back up 4. So I have to go this way, 1, 2, 3, 4. So this is the point, negative 4, 7 pi over 6. I rotated around 7 pi over 6, standing there, turned that far, but then I walked backwards 4. Okay? So let's try a negative, negative, but let's do an easy one. Let's do negative 2, negative pi over 2. So negative pi over 2 just means I'm down here, yes? I'm facing this way. A negative 2 means instead of going here, positive 2 units out, I'm going to back up 2. All right, so if this was point P, I wound up here. Does anybody realize what we've just done? We could have a positive name for that. We have created a system, or there is a system created, where every point has infinite names. Instead of going over 2 and up 2 and everybody getting the same spot, okay, every name goes to a unique place, but every place doesn't have a unique name. You can get there by different ways, okay? So part of the assignment today is going to be to come up with some of those names. Let's just do one right now, and then we'll talk more about this in a minute. I'll give you some examples. But this spot P, Miguel said that we could have a positive name for that. What would the positive name for that one be? Yeah, it would be a positive 2 on a positive pi over 2, yes? Okay, so that's a possible name. What about this other blue spot right over here? Instead of going negative 3 pi over 4 and out 3, we could have gone positive 5 pi over 4 and out 3, positive 3. Okay? More of that later. All right, here's an example done on your sheet for you. They went around pi over 4 and out 3. Notice this circle is 1, this guy right here, then 2, and then 3. Everybody okay? For some reason, I always have to be careful because I want to skip that first one and not call it 1. I don't know what's wrong with me. All right, this one is an example on your sheet of a negative, and it's in degrees, which is nice, but they do very few of these in degrees. They went 120 this way, and then they backed up. Here would be 1, 2, 3, so they stopped at 2.5 right there. Everybody okay? Guys, phones away, please. All right. They also do some of these without actually using the graph paper. I just want to show you an example. I gave you graph paper on worksheet 5. If you wanted to draw this, you would just say I went around 45 degrees and this now has a distance out to here of 2. Does that make sense? Okay, so if you wanted to draw this one, you'd have to draw, I went around 2 pi over 3, but then I backed up 1.5. I gave you graph paper, so this isn't really an issue. I'm going to skip that slide for that reason. That's just another example. All right, you think you're getting the hang of it? I'll do 2 more examples, and then we'll do the ones on your sheet. Negative 7 pi over 6. Well, positive 7 pi over 6 is all the way around to here, which was just past pi, 2 little marks, or the first one that's labeled, right? So a negative 7 pi over 6 would be going this way the first time past pi, which is to here, right? The first. So this is the same as negative 7 pi over 6. Again, change it to degrees if you need to, add 360, change it back to radians, blah. Whatever you need to do so that you can figure out which one we're on. And then 1.5 would just be 1.5. Right there would be point R. And that's how you're going to do it in your homework. Just label it with the R. All right, 135 would be here. Yes, guys? Halfway to 30 is 15, so these are each 15. Everybody okay? But we're going negative 135. So where's that at? Yes, because it's 135 this way, or you could just add 360 to that and you'd get 225. So it's here. We're going to call this axis negative 135. And then we're going to go out negative 2. Is that going to be here? No. What do I have to do? Back up. So it's going to be back here on this, which is actually the 45 line, right? It's the same line, though. And we backed up 2, so that would be point S. All right, let's try the ones on your worksheet. Tell me what to do.
Turn 30 degrees. Or 60.
Okay, we're going to go to this line and go out 1, 2, 3 and label it R. Number 2, these are a struggle, guys. I understand that. When you have radians and we don't think well and then they're in negatives and it's just kind of torturous. But if you just look at the graph and it's one that's labeled, 4 pi over 3 in a positive direction went pi and 2 more labeled ones, right? So if we're going negative, we'd go pi and 2 more. It would be here. Is everybody okay that this is the same as negative 4 pi over 3? Yeah. You can add 2 pi to get another name for it in a positive if you wanted. All right, and then I'm supposed to go on that 1, 2, 3, 4. Everybody get that spot already? Okay, number 3. Tell me which way to go. Where do I stop? How far out? Okay, negative 150 is here at 210. Yep. Then what? And you know what? And I have trouble with that. If you, and I especially have trouble with my slate trying to make that, but the straight line is 30, right? If we add 180 to negative 150. So on that, we're supposed to back up 2.5. Everybody okay that that's where A should be? Yeah. So that would be a really easy one to give another name for. Can anybody give me another name? 2.5, 30 would be another name for that spot, right? A much easier name probably for most of us. All right. This idea of multiple names for the same point, okay, if it's in degrees, we could just add 360 and we'd get another name. Unfortunately, they're not going to let us just do that. They're going to say we could go the other direction, but they want us to come up with one, and I'll show you how they're going to restrict this. But the other thing, if it's in degrees, we could move 180 and back up, or we could go the other way 180 and back up. Lots of possibilities. In radians, it's going to take some thought. Let's do an easy one in degrees first. Point T is up here at 4,135. This restriction is telling us we can't just add and subtract 360, okay, to find more answers. Basically, there's a positive answer, a positive negative, a negative positive, and a negative negative. With numbers less than 360, between negative 360 and 360. They gave us the positive of 4,135. Have I lost anybody yet? Okay, they gave us T right here is at 135 and out 4. We need 3 more names, And I don't care what order we do them in. Can anybody come up with another name for that? Okay, if I subtract 180, I get negative 45. So if I went negative 45, I'd be over here. What would I then have to do to get back to that spot? Back up 4. So you probably did the hardest one first. You came up with the negative negative. Okay. Right there. Okay, so we could go negative to here and back up. We good? All right, what else do you want to try? What if we go back and talk about this original one? How could I have gotten to this 135 line if I had been going this way? Subtract 360, which is negative 225. So if I'd gone negative 225, I still would have been facing the right way and gone out positive 4. So that one is a positive negative. All right, that leaves us a negative positive. If we went around a positive direction, where would we stop so that we had to back up 4? 315, yep. If we went around to 315, then we would back up 4. Okay? And you don't have to put them in any particular order. I kind of crammed that one in there, but all right. Let's try this. I think you have this, yes? Do you have this? And there's no graph for it? Is that right?
Yeah.
There's not really one given. We can look at some of the other graphs around it to help us think. I'm going to go ahead and put one on here, I think. Is this one in degrees? Okay. It just helps, I think, if we can look at the graph as we do it. Yeah, it is interesting. I don't have an answer for that. I have to think about that. That's a great question. This one is around 240 and out 5. I don't even know if my graph paper goes to 5, does it? 1, 2, 3, 4, 5. Yes, this particular one does. On the homework, there's a question where the graph paper only goes out 4 and the answer goes out 5. Just put it on the, past a little ways. It's fine. I finally found some bigger graph paper, but all right. I need some other names. What do you want to start with? How about if we just go this way? How many degrees is it that way? 240 would be the same as negative 120. And if we're at that same axis or pole, we just, at that same line, we just go out 5, right? Okay, so there's a positive negative name. Now, what if I wanted to go in the positive direction and stop and back up? What is this line called? Yes, I'd go 60, and then I would back up 5. So now we have a negative positive. Okay, at that same place, what if I still wanted to stop here? I would have had to go all the way around here, which would be negative 300, and then back up 5. Okay? Yeah, it said just 3 more. All right, let me see if I can find a graph paper in radians for us here. Oh, I didn't like that. I thought I copied it. All right, sorry, it wasn't a very efficient use of our time, but this says pi over 6 and out 2. So right there's the point we're talking about. Josh, can you give me another name? I know it's kind of harder in radians. I went this way. If I if I subtract pi, I'd get negative 5 pi over 6, right? Which would be to here, and then back up 2. You're a genius, Josh. That's like the hardest one to my thinking. But tell me what you want to do, because I don't understand why that restriction is what it is either.
I was going to 7 pi 6, because you go 7 pi 6 and then negative 2, that work, except as pi.
Yeah, I think that's what, yeah, I think this is not right. Okay, Miguel's noticing that this restricts us to pi, but I think they did, and I'll have to look at some of the other ones, but most of us would have said we could have just gone around. Oh, I want to do a different color. I'm sorry. Could have gone around to 7 pi over 6 and then backed up 2. That's equivalent to, you know, the adding 180 and backing up. All right. What about, what do we need? Oh, we need a positive negative. So yes, if we subtract 2 pi, or we started here and went all the way around to there, how far would that be? Yes. And out positive 2. Nicely done, Getty. All right, that's going to take some practice for some of you. If you need to change them into degrees, if the question was in radians, though, your final answer needs to be in radians, okay? All right, graphing polar equations. Going to need a graphing calculator. There are some really fun polar graphs we're going to get to after break. And actually, we're going to look at some of them tomorrow, but we're just going to do them on the calculator. We're not going to really think too hard about them. We're just going to type them in and do some matching. But for today, the only 2 kinds we're going to talk about are circles and lines. Okay, polar graphs of circles and lines. It says an equation expressed in terms of polar coordinates is called a polar equation. For example, r equals 2 sine theta is a polar equation. A polar graph is a set of points that satisfy that. All right. Some equations, guys, in polar are going to look really nice. This equation is really easy to graph in polar. Okay? We're going to get to this. It is equivalent to this equation in rectangular. So it's actually prettier in polar than it is rectangular. Okay? There are equations that are much messier in polar than they are in rectangular. For example, I'd have to think about it, but like x or y equals 2x in polar is like r equals 2 cotangent theta, maybe? I'm not positive that that's right. I'd have to think about that. This would be r sine theta equals 2r cosine theta. To get the, no, that's not right. Anyway, I'll get to some. Sorry, I'm not good at making up stuff on the fly here today, I guess. All right, what we're going to do is we're going to put our calculator in polar mode, but I want you also to do this in radians, because that's what we're going to do most of our graphing in. So polar mode and radians. All right, when you put your calculator in polar mode, Okay, mode. Down, down, down. Radians, enter. Down one more. Over to POL. Enter. Now when you go to y equals, you get some jazz that says r equals. Okay? This is good and bad. It's good because if you have equation in terms of r, you just type it in here. When you hit this button that says x, now you're going to get a theta. Okay? The problem is going to be that when we only have a theta, we can't use this. Just like you could graph x equals things, you can't graph theta equals things in this mode. All right, for this equation, the one we're going to do is just r equals 2, so put in a 2. So in your y equals screen, you just typed r equals 2. Go to window. And again, it's like a parametric, okay? You have to tell it where you want it to try and how many points you want it to try. And then it's going to connect them. If we're in radians, we want it to basically try all the values once around, which is 0 to 2 pi. So your theta min is 0. Your theta max can be 2 pi. If you want to go 7, because it's greater than 2 pi, doesn't matter, okay? Otherwise, you can type 2 pi there. It may already have a value in for your theta step. It actually does, I think, like, I don't know, pi over 12 or something, pi over 15. But just put 0.1, doesn't matter. Then if you do like negative 10 to 10 for the x and negative 10 to 10 for the y, because that's our standard window, you'll get a picture. It's just going to be kind of goofy looking. Does it look more like a ellipse on your paper? Yeah. Okay. But do you notice where it crosses at? It crosses at 2, 2, 2, 2, right? 2, negative 2. So it is a circle. So if we go to zoom and do a zoom square, which changes the window so that it matches the fact that it's longer than it is wide or shorter height than width. It should look more like a circle. Mine is kind of goofy up here because this silly calculator is like scrunched somehow. But does yours look like a pretty good circle? Did you do zoom square? Do a zoom and then is it 5 for zoom square, guys? That makes it pretty nice, okay? What do you think it would be if we wanted a circle that was bigger? If we put in a radius of 3? Because that's all we're getting is a circle whose radius is 2, or a circle whose radius is 3, or a circle whose radius is 5. Pretty easy, right? Okay. Now we got to talk about the other kind of graph that will come up, though. This, if it says theta equals pi over 6, that means we don't care what r is. We want all points where theta is pi over 6. So if I go around pi over 6, I could go out this way or I could go back this way. Does that make sense? So theta equals pi over 6 are all points on this line, who is, what, 30 degrees above here? All points, okay? You get it, Archimedes spiral or something? Yeah. Which is, I think they're related, but yes. All right, so we're going to go to this question on your homework. Do you see this example? They went down 60, but then they went both positive and negative directions and got the line. That's all there is to this. We're just doing lines and circles today. So this one would be outer radius of 4, 1, 2, 3, 4, and draw a circle. Yes? Everybody already got? Oh my goodness. I was just checking if you're awake. That's not even a potato. That was so bad. All right, there we go. This one, go to 3 pi over 4. Which would be here, right? 3 pi over 4 is this line. How did I know that? This is 30 degrees, yes?
Yeah.
So this is 15, so this one is 45, which is pi over 4. So pi over 4 is every 3 lines here, so this would be 2 pi over 4, 3 pi over 4. Use your unit circle, whatever you need to do, okay? And it is a line because it's all R values on there. It's not dotted, it's really solid. I just picked a line that. All right, and what about this guy?
60.
This is negative 300, so it's going this way. Yep, you're right. And then out both directions. Woo, I didn't do a very good job. Everybody okay? That's all you have to do for the homework is lines or circles. All right, there's one more concept on the homework. That concept is the distance between points. If you're an air traffic controller using this system, do you care how far apart 2 planes are?
Yeah.
Maybe. Might care a lot if you're on that plane, right? So, this is not about planes, but the concept is the same. It says somebody was doing landscape design and wanted to do it in polars. Doesn't make any sense to me, but they went 60 degrees, negative 4. Can you plot that on there? Does that seem right? 60, negative 4, 60. All right. And that is where there is a bench. Then there is a pond at 105. Is 105 on here? But we know it'd be somewhere in here, right? 105 would be somewhere in here. And they went out 1. Okay. We need to find the angle between those 2 points so that we can find the distance between those 2 points. If I connect them to the origin, how far was 105 from 180?
75.
Okay. And how far past 180 was this one, which wound up on the 240? 60, yes?
Yep.
Okay. So what is the angle in between them? Okay, here's the bench. And here's the pond. This is 1 unit. This was 4 units. And the angle in between was 135. Can we find this distance now?
Yes.
How? Love cosines. Good job, guys.
I remember that.
What mode does our calculator need to be in? We did this question in degrees, so we got to be in degree mode.
Can it really be true for that graphing?
It can be, but then you need to set your window 0 to 360 because it's got to go all the way around once to finish the graph. One squared plus 4 squared. I'm hopeless at this because I'm blind. Someone gonna do this for me because I can't type on this thing. 1 squared plus 4 squared minus 2 times 1 times 4 times the cosine of 135. So are they 22.7 units apart? That's x squared, right? So I square root that and get 4.8 roughly. It said the distance was in feet right up here. About 4.8 feet apart, so you can sit on the bench and throw rocks in the pond, okay? Pretty exciting. Or bread. That's a good plan. Or fish food or whatever you want to throw. Okay. On your notes, there is a formula. You can use this formula. This question we just did, the 2 points were, guys help me out, was it 4 negative 60 or negative 460? And the other one was, okay. You could use this formula. You would have to put in the R, one of the R's as a negative 4, and the angle between these comes out positive 45, which changes it, which is why we used 135. It cancels each other out. Otherwise, it's the law of cosines. I am not going to give you that formula on a test or quiz. I'm going to assume you can use law of cosines to do this problem, okay? I don't think you should memorize some ridiculous polar formula, and I'm not going to put it on a reference sheet. I just want you to use law of cosines. Do we need to do one more example? Here's an example. It says, what, guys, look at this. This is really easy. What's the angle between those two? 310 and 345. Oh, 35. Thanks. I can't subtract. And so you would do 5 squared plus 6 squared minus 2 times 5 times 6 times cosine of 35, and then square root it, okay? No complicated stuff here. All right, so there's the assignment. If you pull out worksheet 5, it has the graph paper there for you. Did anybody have homework?